My name is Blaine Larry. I'm a student at North Carolina Central University, and I'll be presenting the topic of my graduate research, which is a geomorphological assessment of the Eastern Tennessee Seismic Zone. So just a brief introduction to the Eastern Tennessee Seismic Zone, and from here on out, it's a wordful, so I'm going to refer to it as the ETSZ. So it is a region of seismicity that spans from the northwest corner of Alabama up into southwestern Virginia. And in terms of seismic energy release, it is the second most active continental area east of the Rocky Mountains. So when we think of earthquakes, what you normally consider would be the interaction between two plate tectonic boundaries, whether they're converging, coming together, whether they're diverging, spreading apart, or strike slip where they're grinding past each other. So when we're looking at Tennessee, that's hundreds of kilometers away from the nearest plate margin, and that's what's known as intraplate seismicity. And intraplate seismicity as a whole is not very well understood. It's not quite as straightforward as two plates interacting with each other because we're so far inward in the continent. So intraplate overall is not very well understood, and there are a few other factors particular to this study area that make seismic research even a little bit more difficult, being one, that they're mostly low magnitude, and what scientists do, or earth scientists do, they use what's called tomographic data, where they look at the waves of earthquakes as they travel through the interior of the earth. And based on different properties of those waves, such as velocity or deflection as they pass through different materials, you can sort of, so to speak, map out the interior of the earth, try and figure out what's going on in the subsurface. And that's called tomography, and that's primarily what seismologists and geophysicists will use to try and figure out what's going on that would be causing seismic events. And because we have very poor seismic data in this area, very sparse events, very low magnitude, that doesn't give us good quality tomographic data. And I'm going to do a little bit of a different approach, looking at the landscape that could perhaps fill in a few different holes that we're not able to, different aspects of the seismicity in the area that we're not quite able to obtain through seismic research. And as you can see in the third bullet point here, we got predominantly low magnitude events, and I mentioned as well that they are not very common, so maybe a few a year. So you might consider this to be, why is this important? So there actually is a lot of evidence, despite mostly low magnitude events that don't occur frequently, that within the next, you can't necessarily predict earthquakes, but within the near future, there is evidence that there could be a potentially disastrous event that would affect a large portion of the East Coast. One being, first of all, Tennessee is located on what's called a craton, which represents the most stable part of a continent. It's largely intact, and compared to the West Coast, for example, where they have a lot of earthquake events, all that fracturing in the crust allows the energy from earthquakes to disperse more easily. So let's say you have a magnitude 5 earthquake in California versus in Eastern Tennessee. The earthquake in Tennessee, the energy is going to travel possibly up to 5 times travel 5 times longer than it would on the West Coast. So that's point one. Point two, there is paleoseismic evidence that within the late Pleistocene, which is the last 10,000 years or so, there have been at least 3 magnitude 6 or above earthquakes. Late Pleistocene is about the last 10,000 years, which to us seems like a long time, a geologic time scale. That's a blink of an eye. So that's sort of unnerving because that's a fairly recent event. So this is my study area here. We're going to zoom in a little bit into this block. These are the study watersheds that I used in my analysis, just a blown up view right here. So the goals of my research, so I told you before I was going to take a little bit of a different approach, not using seismic wave data, but I was going to look at the landscape. And we'll get into this a little bit on the next slide, but I'm going to use what's called morphometric indices that are used to quantify landscape shape. And I'm then going to apply some geospatial statistical methods, namely quadrant analysis and correlation, to see if there's any sort of pattern in the landscape that somehow relates to seismicity, perhaps something that the landscape will reveal that will help us to better understand why earthquakes are occurring or identify possibly where future events might occur. And as I said before, we want to use this landscape approach as an alternative to investigations via tomographic research. So here's a little bit better of a description of morphometric indices. So what we do is we use rivers as an indicator for the change in shape of the landscape over time. So rivers are very sensitive to any changes in their environment, and they drastically can modify their properties, whether that's the gradient, channel patterns, any migration of a river through a watershed. And because they're so sensitive to any change in their environment, they can be very valuable for assessing the influence that tectonics places on the landscape. So streams are very good for registering any subsurface movement that makes its way up through the crust and somehow influences the topography. And morphometric indices, all the indices that I use for my study are simply derived from a DEM. So that's simply elevation. And through different methods, you can manipulate the simple values of elevation to derive some pretty complex measurements that can be used to reveal some obscure characteristics of the landscape that you can't necessarily see with the naked eye. So this is my first one. This is called the Hypsometric Integral. And what it is a plot of the relative height against the relative area. And it's a little bit confusing to wrap your mind out of. So it pretty much indicates the percentage of basin that has not yet been eroded, or it's a good way to determine the relative age of a watershed. So when you plot the relative height against the relative drainage area, the hypsometric integral is all this area underneath the curve. And without thinking too hard about it, I'm going to make it very simple. Higher values of your hypsometric integral can be associated with tectonic uplift. So that's what we want to see. We want to see areas where possibly we have very high hypsometric integral values that could tell us, hey, perhaps there's something going on in this section of the Earth that could give us more information about the earthquakes in this area. And this is the methodology that I use to calculate the hypsometric integral. And in the past, this has been a value that's been calculated at the watershed level. So one watershed will have a value, one single value between 0 and 1. I found a MATLAB script online that actually calculates this at the pixel level with the idea that having some spatial variation within each watershed will give us finer resolution and perhaps more detail into individual watersheds that you wouldn't necessarily get if you just assigned one value to each of these watersheds. So these blue lines here, you can't really see them, but those are 349 watersheds. I wrote a Python script that looped through all those. It clipped the DEM to create a DEM with sinks filled. We got flow direction raster, and then I converted that to ASCII format and then used that as the input for that MATLAB script that calculated those hypsometric integral values at the pixel level. And next we got the slope area relationship where, again, we don't have to think about this too hard. So we got S as our slope. K is what we're worried about here. This is known as a steepness index, and that has been proven to be directly related with uplift, just as a hypsometric integral. So if we're going to try to identify any influence of tectonics on the landscape, we want to see some areas where we have very high K values. So really, besides A is drainage area, concavity index, we don't really have to worry about as well. We're just going to take a look at this K value right here. And again, I got the methodology here. The same author that wrote that MATLAB script for the hypsometric integral has one as well for the slope area relationship. So again, I got this Python script here that loops through. We got some flow direction rasters, flow accumulation, and then slope rasters. We convert those all to ASCII format and then stick those into that MATLAB script to get our slope area relationship values at the pixel level. So if you're here before to see Richie's presentation, he used the same methodology called quadrant analysis. And what we do in quadrant analysis, it is an overlay of equally sized areas that you stick over your study area, and it can count the number of features that fall within each of those quadrats. So in our case, it's going to be earthquakes and also the hypsometric integral values and slope area relationship values as an average value per quadrant. And the trick here is that you need an appropriate resolution that is not going to be so large, or it's not going to be so small that you have a whole bunch of quadrants that have a value of 0, but it's not going to be so large that you don't really see much detail on that. We have this formula here where L is the length of the quadrant. You just multiply the area times 2 and then divide it by the number of features, which in our case is earthquake events, and that will give you the length of, or the appropriate length of a quadrant that's both large enough to not have any 0 values, but but small enough that you're going to be able to derive some spatial patterns from that data. And here's a graphic. It's a lot easier to see what I'm talking about here. So we have this grid here, and the ideal size was calculated as 5 kilometers by 5 kilometers. We take our earthquake points and join those to each of these quadrants, and then using the zonal statistics tool, we combine that with hypsometric integral values and the slope area relationship values to reduce the noise, the level of noise in those raw pixel data values. So here's an example here. On the left, we have our earthquake epicenters. There were about 2,500 total earthquakes. And using a point representation, it can be pretty difficult. I mean, you can definitely tell there's some clustering along here, but it can be pretty difficult to tell exactly where those earthquakes are falling. It's much more difficult to derive any sort of spatial pattern because you have, in this cluster, you don't necessarily if there are more underneath. And that's one of the advantages of the quadrant analysis methodology here. There's a much more clear picture with our darker red values indicating a higher amount of earthquakes per quadrant, and those lighter, that pinkish hue, indicating very few earthquakes in the quadrant. And this is definitely more important for our index values. As you can see over here, there's a little bit of pattern, but it just looks like noise. You can't really tell anything from that map there. However, once you get the average of those values through the quadrant analysis, it's much more easy to analyze any spatial patterns you see through here. So green being a low hypsometric integral value and darker red being a high hypsometric integral value. We can see a few lineations of darker colors down at the bottom through here. We see a northeast trending line of lower values through here. And then we got our slope area K values quadrant raster. Again, you're not seeing too much on that left side over there. And this one, I thought had a much better pattern for analysis than the hypsometric integral did. You can definitely tell there's some very high clusters over in the middle eastern section, as well as the upper section as well, with a trend of lower values kind of right down the middle of the study area. So these were the results. So once I had all of those quadrats created for the earthquake count and both of those indices, I did a correlation between the two layers to see if there was any relationship between the values of those quadrats and, the value of the indices and the number of earthquakes. So what I was hoping to find is that for quadrats that had higher earthquake count, I was expecting to see higher indice counts. Looking at these results here, we got our R values that range from -1, which indicates an inverse correlation, to +1, indicating a positive correlation, 0 indicating no relationship. These values don't look too good. They're very close to 0. So though that was a little bit disappointing, to be honest. I didn't necessarily find anything. However, no result is also a result in and of itself. It's possible that because these are the earthquakes in this area are mostly strike slip that are moving past each other, they're not necessarily going to create uplift. So the slope area relationship and the hypsometric integral are designed to identify zones of uplift. If there's no sort of movement in the Earth's subsurface that's causing uplift, then we're not really going to see any pattern in relation to seismicity. However, there is one more thing that I'd like to try, and I found this paper just a few weeks ago, so I'm still in the process of doing this, but I found a group of researchers that proposed this theory of Mansfeld lamination across the southeastern United States, and they believe that this has been the cause of uplift, seismicity, and intraplate volcanism within the southeastern United States here. So this diagram I found, it's not actually representative of the Eastern Tennessee seismic zone. I just wanted to sort of explain what the process of mantle delamination involves. So up here we got our lithosphere, and as you can see right here, there's that sinking layer of what was previously attached to the lithosphere here. And as that lithosphere descends, you have this asthenospheric material that upwells, and that's what could potentially be causing the uplift of the Appalachian Mountain Range. So that is their theory, and I got some tomographic data here, which unfortunately I don't have the data yet. I'm working on getting it. So this small picture is the best I could do. I wasn't really able to zoom in here, but what we're looking at Lower seismic velocities are generally associated with lower seismic velocities are associated with warmer materials that are more buoyant, while higher velocities are associated with denser and cooler material. So we're going to look right at this F5 right here, and you can see all that blue there. That's the proposed site of Mansfeld Lamination. And when I was looking at that image, I noticed with my slope area relationship values that it seemed to match up pretty well with, we should expect to see if that's where the mantle is sinking and we have this hot asthenospheric material uprising causing some change in topography, some increased elevation, then we should see some increase in values along this on these blue sections right here, with lower values concentrated along the red and the yellow. And I thought that matched up pretty well. You can see that streak of, there's some green, yellow, and orange through there that sort of coincides with this section right here. And then you have this these higher hypsometric integral values right here coinciding with that green and blue, which is indicating where that mantle is sinking. So I have yet to gather that data, but I'm hoping run a correlation on this. This could perhaps explain why at least there's uplift. It might not necessarily give us information on earthquakes in the area, but would at least give us another step towards understanding the properties that are governing the landscape in the Appalachians. And here are my references, and I am open for questions. Yes?
I was just, when you went back to, and maybe I missed it, when you were talking about lower seismic velocities, you're speaking of the actual rate of movement, correct?
The rate of movement that a seismic wave travels through material.
So not like the, how, what did they call that, the earthquake?
Magnitude?
The numbers that correlate with the 7.2.
Magnitude scale, Richter scale,
okay.
Yeah.
I teach this stuff, that's different. But, so not so much energy level as just velocity itself.
Right, so we're looking specifically at the rate at which a seismic wave travels through a material.
Okay.
So it doesn't necessarily correlate with magnitude. All right. Yes?
How much does the rate of change for the seismic velocities line up on the different rock types?
So it definitely does depend on the type of material. They used a scale here. There's different ways you can, I'm not totally experienced in the physics of this, to be honest, but you can do different things like add a temperature gradient to your data set. Through different studies, you can assume the type of material that are down there, and you can add all those into your data model. And that's what they did in this research. They took the information they had as far as the geology, temperature gradient as you go deeper within the earth, and the materials that they suspect that at that depth that the earth is composed of. But yes, it definitely will affect the velocities. Is that it? Okay.